Hello, welcome back to Math 332, section 1.8, the second part of the presentations. So because this section is long, so I decided to break this video into two parts. So in the first part of the presentations, we look at the concept of transformations, which is nothing but mapping. We did spend a little bit time to look at the set builder notations, which is something that you're going to use throughout this semester. So make sure you do know what set is and how to write down the set by using the set builder notations. We seen a lot of we have actually looked at a lot of the example of transformations, and in particular, there's a type of transformations which is very important. The type of transformation is called matrix transformations. And matrix transformations is all the transformations that can be written in this form. So if you can write a transformation in this form where A is a matrix, then you call that transformation a matrix transformations. And we also talk about the definitions of linear transformations. So being linear, you have to satisfy the additive property and homogeneity property. And also that we mentioned that in order to show this, you cannot pick a special example. You actually have to show that this additive property and homogeneity property actually hold for all the elements in this set, all elements in this set, and also for all real numbers. And how do you be able to do that? Well, the way to do it is to make sure that you make no special assumptions, on the things that you try to show. You make no special assumption on what this matrix A, and so on and so forth. To show something is not linear is easy because you can find a counter example. So this is the example that we look at, the one method to show something is not linear. We can also find a counter example, which is specific instances where the homogeneity property and the additive property fail to hold. So for showing something is not linear transformations, you can basically just look at the you can find some counter example. You can argue by a special case, right? You can argue by invoking some special number, some particular matrices and stuff like that. But to show something is linear, you cannot make any assumption on all these matrices because you're supposed to show that this homogeneity property and the additive property holds for all elements in this set. So you cannot make any special assumptions on the type of matrices that you get. You just have to show that in general, if you get an element from this set, it's going to look like this, it's going to look like this, and you want to show the additive property hold, and you want to also show that the homogeneity property hold. So there's a lot of homework problem like this for you to practice. So make sure that you write down your solution very carefully. Speaking of writing down your solutions, if you have a one-page homework solutions, then that is definitely not enough. You definitely miss a lot of stuff. You're not doing things very carefully, because if you do things very carefully, there's just no way for the homework to fit in one page. All right, so make sure you do your homework properly. And right now in the second part of the presentation, we are actually going to look at a very important theorem in linear algebra, which kind of like characterize what type of transformation is linear. So the theorem 1.8.2 in your book says that if you have T, a mapping from Rn to Rm, that mapping is a matrix transformation. It's a matrix transformation, meaning that it is a transformation of this type. It's a matrix transformation if and only if this mapping have satisfied these two conditions, which is the additive property and homogeneity property. So a matrix transformation is a matrix transformation if and only if you have these two property. And you should by now see that these two property basically is the definitions of some transformation being linear. So another way to say this theorem is this, which is some transformations, given a transformations, that transformation is a matrix transformations if and only if it is linear. Now, why is this important? Because actually one side of the statement is actually pretty obvious, which is this side right here. Let's look at the proof real quick. So this is a statement of the theorem. It says that if you have a matrix transformations, if you have a transformation, the transformation is a matrix transformations if and only if that transformation is linear. Let me say that one more time. which is that if you have a transformation, okay, you don't know what that transformation is. You have a transformation. This transformation is a matrix transformation if and only if that transformation is a linear transformation. Now, what it means is this. So one direction of the proof is easy, which is, let's say we try to prove from this side. This is a theorem. Definitely, we all have to look at the proof. So if you look at proof from this side, this is the obvious part. What it says is that if the T is a matrix transformation, okay, right, you go this way, right? So if T is a matrix transformation, we want to show that that transformation, the matrix transformation, is linear. That is redundant actually, because we already know that. So if you have a transformation, okay, it's a transformation is a matrix transformation. Of course, it's linear because by definition, something being a matrix transformation, meaning that there exists a matrix such that that transformation is in this form. That's the definition of some transformation being a matrix transformation. And once you have a transformation in this form, property number 1 and 2, the additive property and the homogeneity property will hold for sure, because from matrix arithmetic, we already know that for a property of matrices allows you to do all this. Therefore, 1 and 2 is trivially true. These are true trivially because for a mapping that has this form invoking a matrix, all this property will follow pretty easily from the properties of matrix multiplications, and also scalar matrix multiplications. So that's not going to be a problem. The important part is the reverse. The reverse is not that obvious, meaning that, so the reverse saying that if you have a transformation, so the reverse saying that if you have a transformation and that transformation is linear meaning that they satisfy these two conditions. So if you have transformations satisfy that two conditions, that transformations must be, there's no other choice, that transformations must be a matrix transformations, which means that that transformations, okay, they must exist a matrix A such that that transformation T of X is that matrix A multiply X. So that is the part which is not obvious, okay, because being a matrix transformation definitely is linear, but being linear, how do you know that it is a matrix transformation? Okay, being linear means that satisfying condition 1 and 2. So if you have a transformation satisfy condition 1 and 2, how will you know that that transformations must be a matrix transformations? Okay, so that's what we try to prove. So how do you actually prove that? Okay, so that's a statement. So suppose that we have 1 and 2, the property 1 and 2, making the transformation linear. We want to show that there is some kind of matrix A such that that transformation is in the form of AX. Okay, you want it to be in the form of AX. Well, in order to prove something like that, it will be great if you want to show something is a matrix transformations. Well, it will be great if you can find that matrix. Okay, if you can find that matrix, then everything will be cool. So, so in order to establish this proof, we are going to find that matrix A. So, right. So before we do that, let's introduce some notations. This is a common notation that we're going to use throughout this course. So, suppose you are in Rn, which is what we have right here. So do not make any special assumption that this is R2, okay? Because you want to show this thing is in Rn. So this is definitely an entries in Rn. Rn is the n by 1 column vectors. So suppose you have n by 1 column vectors. So suppose you have n row here where the first entry is 1, but the rest, they are all 0. So if you have a matrix, n by 1 column matrix, which we call the column vectors, where the first entry is 1, the rest is 0, we call that E1. Okay, similarly, if you have n by 1 column vectors where the first entry is 0, third entry is 0, in fact, everything is 0 except the second entry, then you call this vectors E2. Okay, so EI will be everything 0 except the entry on the I row. They are not 0, and not only they are not 0, they are 1. They are taking the value 1. And EN will be everything 0. The last entry is 1. So these are all elements in Rn. So I claim, you don't know that yet, we will show that, but I claim, okay, or we claim, okay, that the matrix A consists of TE1. So we know that T takes Rn's to Rm, right? So TE1 is defined. I don't know what that value is, but I know that this guy here is an element in Rm, which means that this guy here is a m by 1 column vectors. Okay, I don't know what that thing is yet, but I know it's a m by 1 column vectors. I take that column vectors and put it right here. So I use these notations, okay? So instead of writing just TE1, I'm writing TE1 like this to indicate that actually it's a column vector. This is a column vectors, and I call it TE1. So TE1 is defined, okay? I have a mapping that take Rn to Rm, so you take all the elements in Rn and then map it to Rm. So TE1 obviously defined is something. I don't know what that thing is, but I decided to put it as the first column of my matrix A. I'm doing the same thing for TE2. So I have E2. So E2 is known. This is E2. But TE2 is not known. You don't know what that thing is. So but you know it's an m by 1 column vectors. Take that entire column vectors and put it in the second column of matrix A. And so on and so forth. So the last column here is TEM. Now, so my matrix A is constructed this way. This is how I construct my matrix A. It consists of all these m by 1 column vectors, m by 1 column vectors, m by 1 column vectors. So we know the size of this matrix actually. How many rows do we have? So the number of row will be, so TE1, right, is in Rm. So have m row. So have m row. So have m row. So this matrix have size m by how many column? Obviously 1 column, 2 column, all the way to n column. So this is an m by 1 matrix. So matrix A here is of size m by n. Yes, okay, m by n. Now, so I'm claiming that having this matrix A, that transformations T that satisfy condition 1 and 2, which is additive property and homogeneity property, will be written as these matrix multiplications. Okay, so how do we prove that claim? So this is the proof of that claim, which is I'm going to take an arbitrary but fixed element in Rn. Now you see this a lot also, which means that I am taking an element in Rn. I don't know what that element is. It's any elements in Rn, but it's very difficult for your mind to concentrate on any. So I'm just saying that I pick an arbitrary element in Rn, but I'm fixing it. So throughout all this computation, this x never changed. It's something that is arbitrarily chosen from Rn, but once it's chosen, I am not going to change it. That's the meaning of but fixed. So once we have this x, okay, their entry is x1, x2, all the way to xn. So that's the entries. So this x in Rn, which is a n by 1 column vectors, can be written as this linear combination of your E1, E2, all the ways to En. Now these are all something that we call bases. But we will again look at this in later chapters. We are going to look at this concept of bases and dimensions in detail. But right now, you don't even need to know that name, what basis is. I'm just telling you that it's called basis. So just make sure that you agree that these expressions right here can be written as this form. Okay, can be written as a linear combinations of the combinations of. Okay, you also do not know what linear combination means yet, but it means that combination that looks like this. Okay, so you can see the x, which is from Rn, can be written in this form. This is critical, and because we already call this E1, E2 to En, so this whole thing here can be rewritten as this. Okay, cool. So given x in Rn, I can write in this form. So this, again, be very careful. This one is a number, but this one is not a number. This is actually a m by 1 column vectors. Okay, so we have to be careful about notations. So usually, if sometimes they use this notation, but as I said, if things are clear, how do you know it's clear? Because I spell it out for you. Okay, this is E1, E2, and so on. So it's clear. So this is vectors. So x can be written as this. Now, we know that T satisfies the additive and homogeneity property. So I don't know what that T is, but I know it satisfies the additive and homogeneity property. I know x can be written as this. Okay, so I'm applying the homogeneity and additive property. And again, so the homogeneity property and additive property here, especially the additive property, is written for only 2 vectors, but as long as it's finite, not infinite, okay, like number of u, v, w is not u plus v plus w plus dot dot dot, and if it is just finite, all these things is still true. So the additive property like that still true. Oh no, what's going on? Okay, right, still true. So I can deal with n elements just as long as it's not infinitely many elements. So I'm applying my additive property right here. I'm actually, yeah, I skip a step here. So additive property will just simply mean x1 e1 plus all the ways to xn en. And because x, these are numbers, so I can take that thing out by the second property, the homogeneity property. That's the reason why you see that you have that. Okay, so you see that you have that. Now, so make no mistakes. Pretty sure that you can see now that Tx is this. Now, remember in the first video when we talk about matrix operations, this thing here is actually right here. They are the same thing. The column pictures that I mentioned, remember? So this is actually a column vectors, a column vectors, a column vectors. Okay, so if you put the column vectors right here and multiply with this number, okay, x1 number, x2 number, x3 number, these multiplications give you, what does this multiplication give you? It gives you this. Therefore, you see that your Tx, as long as it satisfies the additive and homogeneity property, it will be written as this matrix of that x. This matrix is what we call A before. So you do show that if it's linear, it is a matrix transformation. Okay, right. So that's it. That's the end of the proof. Okay, you actually only need to prove the second part because the first part, the first direction here is actually trivial. Something being matrix transformations means that it's linear. That's true, no big deal. But something being linear implies that it is actually a matrix transformation. It is not so clear. Okay. In fact, let me show you this one more time. This thing here, I mean, you should know by now, but actually in this notes, you actually saw it before. It is right here when we talk about matrix transformation. See that? See that? So this is the same as you putting the column 1, 5, 9, 2, 6, 10, and so on and so forth in here. And then here the x1, x2, x3, x4 is this number. So this is what we call the column pictures matrix multiplications. All right, so that's the end of the proof. Questions. Let's look at one example before we look at the implications. This have far-reaching implications. We can use it to do a lot of stuff. So right now, let's just look at how we apply this theorem, the easiest one. So suppose you are having a mapping from R3 to R3. This mapping is linear. Okay, so if this mapping is linear, so if this mapping is known to be linear, it's a linear mapping, which means that it satisfies the additive and homogeneity property. We want to show that this linear map is actually a matrix transformation. So we want to show that this transformation T is actually of this form. So we need to construct that matrix. And how do we do that? So suppose the TE1 give you TE1, we are in R3, so E1 will be 1, 0, 0. So TE1 is 1, 2, 3, for example. TE2, these are given. Okay, these are given from the questions. So TE2 is this, TE3 is this. Then what is the matrix in the matrix transformations? Well, it will be the 1, 2, 3 coming from TE1. So TE1 is 1, 2, 3. Put it 1, 2, 3 right here. Drop the bracket. Just need the number 1, 2, 3. TE2 is 0, 1, 2. Drop the brackets. Just put here 0, 1, 2. Drop this parenthesis. Okay, and then TE3. What is TE3? That's 1, 1, 1. Just put it right here. Then this is the matrix A for that linear transformations. So given T linear with this information, we know that it is actually of matrix transformations, and that matrix, which is sometimes also referred to as a standard matrix, is this. Okay, right. So that's what the theorem say. If it's linear, it's definitely like that. Oh, by the way, so if you look at the theorem very carefully, it says that we are only looking in the space of Rn to Rm. For your information, this theorem is also true, not for the Rn and Rm, but for any finite dimensional vector spaces. So it doesn't really have to be that. But for this is just an introductory linear algebra, so we don't want to make the situation very complicated. So we are going to concentrate on Rn and Rm every time we want to use theorems 1.8.2. But for infinite dimensional spaces, things are a little bit more complicated, but this theorem also true for finite dimensional spaces. You will know what that thing means, what finite dimensional means halfway through the semester. I promise. Okay, so that is, let's look at some of the very important implications on how to use this theorem. So we want to look at transformations that rotate something. So for example, you have come across all this type of stuff before. Let's see. So for example, let me take out the Mathematica. So this is the, oh no. All right, so this is not good because, right, never anticipate this problem. Never mind. Okay, right, sorry. So let's look at, say for example, right here. So this is a picture of my imaginary friend. He's actually right in front of me on my table. I call this guy Buddy. He's my imaginary friend who helped me go through this terrible winter. Anyway, so you have seen this kind of operation before in the software. You use it all the time, which is that you can rotate it. Okay, you can rotate it. You can rotate it. You can rotate it. So how do you make that happen? So in order to rotate something like this, can I write on top of it? No. Okay. Right, I was hoping. So if you want to rotate something like this, you kind of have to rotate every point. Every point, every XY coordinates, no. So every XY coordinates you have on that picture has to rotate so that you can have the entire thing rotates by 90 degrees or by 180 degrees, so on and so forth, right? So how do you do that? Well, we can do that with no problem. Okay, hang on a second. Where is my notes? So right here. So, right. Okay, so suppose you want to rotate that picture by 90 degrees counterclockwise, that directions, and by 90 degrees. So for every coordinates, you will have to rotate it. Okay, for every coordinate, you have to rotate. If you're here, you have to rotate 90 degrees, something like that. So if you, instead of, so kind of like in order to write programs to ask the computers to rotate a picture for by 90 degrees, you kind of have to write infinitely many codes to figure out how all that coordinate changes. But having that theorem that we have before, you actually do not need to do that. You actually only need to know what happens to your TE1 and TE2. Okay, I'm not sure whether you see this because what it says is that, as you can see right here in the proof, it's hidden in the proof. But if you see, okay, but if you see in this proof, okay, so we have a transformation. Okay, so suppose we have a transformation. We don't know what that transformation is, but if you can see, if we can find out what that transformations do to this E1, E2, and EN, like E1, E2, all the way to EN, you only need to figure out what the transformation do to these vectors, n of them, only n of them. Then you actually know everything about that transformations because you know that Tx is equal to Ax. So this time, in this formula here, the x is not E1 anymore. It can be anything. It's not E1, it's not E2 anymore. It can be anything, which means that knowing this n informations, you now know everything about that transformations. Everything, okay? So that is the power of this theorem. In fact, not really that power, but the statement of the theorem, but it's the proof of the thing, which means, so same thing here. For example, this example that we saw just now, only knowing this 3 mapping, only knowing what the T does to do to these, if you have E1, E2, and E3, only knowing what happens to TE1, TE2, and TE3, we now know everything about the mapping. X can be anything now. It doesn't have to be that. Like, for example, I would know what happened to T157. I know that because it's just taking that matrix multiply 157, so on and so forth. All right. So for rotations, for that transformations to rotate a picture by 90 degrees counterclockwise, center at the origin, I actually do not need to know every single coordinate, the change of the coordinate. I don't need to know every one of them. I just need to know what happened to TE1 and TE2. So what is E1? This is R2, so we are in R2, so E1 is nothing but 1, 0, and E2 is nothing but 0, 1. For those who are taking calculus, I think you should know in terms of vectors, this is your I vectors, and this is your J vectors. Remember, your I vectors is going to be like this guy, and J vectors is going to be this. So in order to make sure, in order to get the rotations transformations, I just need to know what happens to TE1, which is our T1, 0. And I know that pretty easily is 0, 1, because if you have E1 right here, which is 1, 0, if you want to rotate 90 degrees, isn't it that after you do the transformation, the TE1 will be right here? Okay, E1 is here, but you want to rotate it by performing this transformation T. Our T here is a transformation that rotates the object by 90 degrees counterclockwise, center at origins. So if E1 is right here, 1, 0, okay, and then TE1 will be 0, 1, because what is this vectors? This is your J vectors, right? So this is 0, 1, right? 0, 1. So that's how we got this. Okay, so what is TE2? Well, so what is TE2? So can I erase this? Okay, so that I can use that again. So I need to know what happens to this E2. So E2 originally is here. That's our 0, 1. What happened after you rotate it 90 degrees counterclockwise, center here? So your TE2 is right here. You follow? Your E2 is here. Your TE2 is right here. So how do you describe these vectors? Which has magnitude 1 but pointing in that direction? Well, the answer is negative 1, 0. Remember that for general vectors, if you have vectors A, B, what it means is that you move in this direction by A unit, and then you move outward by B unit, right? So this one, we don't have any vertical movement. We only have the horizontal movement. You move negative 1 because you are moving 1 unit to the right-hand side. So you have this vector. So TE2 is that. So so the matrix transformation associated with that rotations is TE1 and TE2, which give you this, which is this. So now I know what are the coordinates for everything that is supposed to rotate 90 degrees counterclockwise. So for example, what happened to coordinate 5, 7 after you rotate it by 90 degrees? Well, I just have to compute this. This is 0, negative 1, 1, 0, and 5, 7, and I get the answers. Okay, I don't have to compute this again, because actually I already know everything that is on R2. I know the image of every element in R2 after you rotate it 90 degree counterclockwise. So that's a power, one very important implications of that theorem. Okay, right. So let's see how we are going to use this for general rotations. So suppose you have you want to find transformations, and we can show that all these transformation, rotation, and all that are linear. We don't want to talk about it right now. You can kind of just assume it, that I'm telling you it's a fact that all this rotation operation and all that is actually linear operation. Okay, because if it's not linear, then you get into trouble. You cannot really apply those techniques. Okay, so now we have to find out transformations that make a rotation of angle theta counterclockwise, center at the origins. So again, how do you write the matrix that lets you do all these transformations? So, well, let's figure out what is TE1. So E1 is right here again, but right now TE1 is going to be rotated by theta degree. So this is your E1, and then after you rotate it, you have TE1, which is right here. Okay, so how do you find the vectors? Well, preschool trigonometric functions, using that preschool trigonometric functions, you know that the concept of trig, right? So you here move here like cosine theta units, move here sine theta units. If this is theta, this is unit 1, by the way. The hypotenuse is 1. This is 90 degrees. So if you have the hypotenuse is 1 and this is 90 degrees, we know that using the ratios, this is cosine theta, because cosine theta is this entries here, this x over the hypotenuse. So if you call this x, as obviously as you can see, x is cosine theta. Do the same thing for the y. You have that y is actually sine theta. So this TE1 is actually cosine theta. Move cosine theta unit here, and then move sine theta in the upward directions. So TE1 is this. Okay. Well, where is your E2? Well, your E2 is right here. So what happened after you rotate it 90 theta degrees counterclockwise? So that is your TE2. So that is your TE2. So how do you write TE2? Well, in terms of its magnitude, this side here is cosine theta, this side here is sine theta. So you will have to move here negative sine theta, and then move upwards cosine theta. So the vectors TE2, the vectors TE2 is in this form. I'm assuming you know how to deal with vectors. This is like the things that you learn in Calc 1, and you have taken physics or whatever, or engineering students. Obviously, you by now this is like second nature to you. So I would not mention, so like I would not go into the detail right here, just telling you that, well, you should know that TE2, if this is TE2, TE2 is negative sine theta in the x directions, and in the y direction you have cosine theta. So the whole transformations can be captured by writing it as Tx equals to Ax, with A as the standard matrix TE1 and then TE2. So now I can figure out what happens to any coordinates. So if theta is given, say whatever angle you want, 32 degree or whatever, so I would be able to know what T25 move after moving that rotation of 32 degrees. So here will be like cosine 32 degrees, so on and so forth. Okay, so you get a lot of opportunity to practice writing down all these special matrices in that transformations. Your homework, like for example, homework problem number 9, number 10, and actually number 11, all kind of require you to utilize this fact. So knowing that TE1, once you know the standard basis, these are the what we call the standard basis. Once you know what happens to the image of those mapping of those standard matrix, you know actually exactly what is going to happen for that general linear transformations. Okay, so one last thing, which is this problem. So this problem here traditionally gives students a lot of headache. So that's the reason why I included hints here. You doesn't really have to follow the hint, but having the hints is kind of easy if you know what's going on. So we are still following the same procedures. If you look at these questions, it says that you want to find a matrix representations for transformations that is a reflections of the plane in the line y equals to 2x, meaning that you have a transformations which will take a point right here, for example, and reflect it across this line to another point right here, so that this is 90 degrees. So you have y equals to 2x. You want to find the transformations, the matrix, okay, that represent this transformation. So we want to find this matrix that represent the transformations. What that transformation do is that you have a line y equal to 2x, and every time you have a point here, you want it to reflect that across this y equal to 2x. Okay, so that this is like equal distance, and obviously has to be orthogonal, which means this has to be 90 degrees. So if you have a point here, then it will be get mapped to here. If you have a point here, get mapped to here, so on and so forth. So now you know what that transformation do. Question is, how do you find that matrix? All right. So from our previous discussions, I'm pretty sure that you are very confident. You say that, well, if I have my E1, this is R2, so E1 is obvious is this. E2, if you have this, then if I can figure out what TE1 is, okay, if I can figure out what TE2 is, then I know the matrix. This is going to be the matrix. This is going to be a TE1. This is going to be TE2. Now, you are exactly right. This is what we are going to do, but that is a problem. The problem is that, okay, the E1 is right here, okay? So what happened after the reflections? It's not so easy to see, right? I have no idea what happens after that. So TE1 is not simple. It's not something that is so, like TE1 from the example before is pretty easy because we know this is your E1. So if you rotate theta, so this is TE1. But this is not like that. If this is E1, what happened to that? I mean, it is still possible to find what TE1 is. You can use geometry or something to help you to figure out what is TE1, which is reflections of across this line. But there's you can do that. There's not a problem. You can figure out what TE1 and TE2 using that method. Another way is that let's change perspective a little bit. So instead of working with E1 and E2, we want to work with B1 and B2. Now, B1 is nothing but a vector that is on this line, and B2 is nothing but a vector that is orthogonal to this line. Try to make sure that you know why. I know that B1 is on this line and B2 is perpendicular, orthogonal to that line. Make sure you know why. So if I have my B1 like this and B2 like this, then I know what that transformation is. By the way, in this question, the transformation is L instead of T. So that's L. So I mean, if my B1 is on this line, then obviously my LB1 will be still same thing, because what happens to the reflections across this line if you're on this line? Well, you're not doing anything. You just stay right there. So your LB1 will be B1, which is this. LB2 will be a little bit, I mean, it's still easy because it's just like orthogonal to that. So you just have to figure out what this thing is. So you can figure out what this LB2 is. That's a hint. Figure out what this thing is. So you have a number for this. You have a vectors for this. And then still we have to find LE1 and LE2. So that's the key. That's LE1 and LE2. Now, using a techniques that you're going to be very familiar with, these techniques eventually, is that I need to know what LE1 is and I need to know LE2 is. So I write down my E1, which is this. I know my B1 and B2, by the way. B1, B2 is known. So if you can figure out what kind of numbers, what type of alpha 1 and alpha 2 you need in order to get this equality, so you have to compute what alpha 1 and alpha 2 is. That's easy because that's solving system of equation with 2 equations and 2 unknowns. So anyone can do that. So just make sure that you can find out what alpha 1 and alpha 2 is. Then, so alpha 1 and alpha 2 eventually are known numbers. These are known. Okay, you just have to figure that thing out. And L is a linear operations. So LE1 will be L of alpha 1. So LE1 will be L of alpha 1 B1 plus alpha 2 B2. So you can split it by taking alpha 1, which is a number, and B1 are vectors. So alpha 2 LB2. So you can split into things like that. And by the way, this is known, so you can compute what is LE1. So LE1 will be known once you have alpha 1, alpha 2 figured out. Same thing too. The E2 you can write as the combination of B1 and B2. So figure out what is these two numbers, alpha 3 and alpha 4. So it's just solving system of 2 equations on 2 unknown. It's kid stuff. So eventually alpha 3 and alpha 4 will be known. So again, apply linear property on L. So with alpha 3 and alpha 4 are known values, L1, L1, 2 and L -2, 1 are also known numbers, then you can figure out what is this value. And in order to answer that question, you just have to put it as the columns of your matrix A, then we are done. So, so that's basically all of what you need to know for these sections for taking the exam, the test on Tuesday. Is that first part of the video tells you all the example, how do you show something is linear, something is not linear. And this part here basically tells you that if the operations, the transformation is linear, you can figure out entirely exactly everything about that transformations if you know what happens to TE1 and TE2 and in general all the way to TEN if you are in Rn. Okay, so meaning that this is actually pretty powerful because it's like right when you try to write a code or something to rotate an object or to reflect an object, you don't have to worry about every single coordinate because you have a formula for that, and finding that formula does not require you to look at the transformation of every single vectors. As long as you know what happens to these standard basis vectors, if you know the image of the standard basis vectors under that mapping T, then you know everything about that transformations. And these are the homework to solidify this concept, and it's actually something that is pretty important for you to know. And that's it. This is the things that you missed because of the shutdown. And now, well, that's it. It's getting late. It's snowing outside, and I need to get out of this office. And so I see you on Tuesday. Bye.